Good morning, everyone. Thank you for joining this webinar. So today I will be talking on the coastal circulation around India. So most part of my talk will be on the modeling of coastal circulation, particularly the east coast of India, the East India coastal current and its modeling. And myself, Dr. Francis from INCOIS. I work in the field of ocean modeling and see how the models can be made use for operational purposes. So if you look at the coastal circulation, particularly the east coast, the earliest observations, of course we had a very few observations in 80s and even 90s on the currents in the Bay of Bengal. So there are some ship observations or ship drift data which was compiled by Cutler and Shalom. And if you look at these observations, in fact Dr. Shetty has put up these observations into maps to see what is the circulation in the Bay of Bengal. And it's very interesting that even in the early 90s, we could see the signals of strong coastal currents. If you look at the graph in the left hand side, you will see that there are arrows which are flowing or directed to south in November, and in April it's mostly directed to the north or poleward, and in July and August months things are a little complicated. There are arrows which are northward, as well as we have arrows something which is southward also. So this is the earliest understanding of the coastal circulation. You can see that the data is very sparse, and there were some observations of salinity also from the cruise data and other observations. So that also suggests that there is a pattern of equatorward flow of this low saline water. That is what you see in the middle panel. And you can see that there are lots of variability in the dynamic topography in the coastal waters. That gives an indication that there is some strong current in the eastern east coast or the western Bay of Bengal. These western boundary currents are later called as East India coastal currents. Another interesting observation by Dr. Shetty's team again in 1991 is they looked at the hydrographic data in the east coast. They have looked at the cross shore sections of temperature and salinity. What they have noted is that there are regions where we have upwelling, but then below that, maybe something like 50 to 70 meters, we have regions of upwelling, but below that there are signals of downwelling. This gave an indication that there are regions, the surface flow may be in one direction and the subsurface flow may be in another directions. So these are intelligent deductions of data, very sparse data at that point of time by the group in National Institute of Oceanography. There was a lot of studies on these coastal currents, both in the east and west coast. So we focus here on the eastern part only. Later in 1996, Shankar again from National Institute of Oceanography gave a better picture of the coastal circulation or Bay of Bengal circulation for that matter. Again, this is based on the ship drift data. They also showed that coastal currents are there, and we can see that the western boundary currents are flowing poleward in one season and equatorward in another season. We can see a lot of variability in this month-to-month variability in this circulation. if you look at the entire Bay of Bengal, the data is quite small. If you see the other locations, other part of the world oceans also. Then there were a few studies, or quite a few studies on the modeling of this circulation. So that was another important part of the studies in 1996. 1990s were very good in terms of studies in the coastal currents. A large group in NIO, Goa, led by Dr. Shetty, has come up with a lot of interesting ideas, both with observations and modeling. But the major part of the modeling studies were with much simpler models, linear models, and they were mostly looking at the different mechanisms what can drive the coastal currents. So they were looking at sensitivity experiments to see what could happen if there are forcing in the central Bay of Bengal, what will happen if there is forcing from the equator. So these kind of sensitivity experiments were being done using the LCS model. It's a linear model, so much simpler model, but they could get a good understanding on this system, and they have identified that most part of the coastal currents were forced by the coastal Kelvin waves, equatorial forcing, and interior bay forcing, and it's quite difficult to distinguish what is causing what. So linear models are quite handy in looking at the individual effects, because they don't interact in a non-linear way. So these these model studies were useful. But in 1996, this was the first ever application of a general circulation model, a complete general circulation model, which is called modular ocean model, the MO. And Professor Vinay Chandran, he was doing his PhD at that time in IAC, so he took up this challenging topic to model the Bay of Bengal using a general circulation model. This was the first ever application of GCM in the Indian Ocean region. And the main objective of this study was to identify the relative role of different forcing. Of course, there were understanding on what are the forcing mechanisms, but now in this particular study, he was more focusing on the relative role of different forcings. And based on the studies, what he came up was that the most important factor or forcing mechanism is, of course, the coastal Kelvin waves, and then comes the equatorial forcing, and then interior bay forcing. So this was a very interesting study and a path-breaking study in terms of ocean circulation modeling in the Indian Ocean. So these were the stories of 90s, and then we have data from satellite. We could get the geostrophic currents, and from the winds we could get the Ekman currents. So we could combine this. There is a beautiful product called OSCAR, which gives the surface circulation. And what you see here as a movie is essentially the circulation in the Bay of Bengal. And it's a animation, spanning for one full year in 2013, and you can see good, or strong flow in along the east coast, and that varies quite a lot. And what is quite interesting is that Bay of Bengal, we all know that is an eddy-rich region, and a large part of the variation in this coastal current also coming from these eddies. Eddies interact with these coastal currents, and the direction as well as the intensity of these current are, to a large extent, are determined by the eddies, position of eddies, their propagation and intensification. So this was an important study, and it gives a little more details that okay, you cannot simply look at the boundary current as a single long stream of flow. It is rather small scale eddies are also embedded in this large scale flow. So this was also an interesting understanding of the ocean circulation or the coastal circulation in the Bay of Bengal. Now, if you summarize this part, that the earlier modeling studies on coastal currents of the east coast of India, particularly in 1990s, this was a golden period for coastal research in India, and that was mostly to identify relative roles of different forcing of EICC, and mainly with the simpler models. And when the Indian Ocean dipole, the classic Indian Ocean dipole, was discovered in 1997, most of the focus of Indian Ocean physical oceanography, at least, have gone to that side. So people started looking at the mechanism of the development, or the dynamics of Indian Ocean dipole, how they get triggered, and how the large scale planetary scale waves make this Indian Ocean dipole intense. What are the Earth interaction processes of Indian Ocean dipole? So this was a good initiative, but it has taken the attention from the coastal studies in the Indian Ocean. So after 1997, you see that the studies are quite low in terms of the coastal circulation. And then it revived after 2010, mainly due to the availability of continuous observation. I will come to this in the next slide. And also we started getting a lot of requests from user community that we need good forecasts of coastal currents, because most of the operational activities in the ocean happens in the coastal region, and they require, in addition to waves, they require good forecasts of currents. So that became another forcing factor to revive our research in the coastal region. Of course, our modeling capability, computational capability, all these things have improved. So this was the forcing. These were the forcing for us to revive the ocean modeling, coastal modeling activities in India. So I was talking about the coastal observations. So in fact, Dr. Shenoy in early 2000s initiated thinking on to have detailed observation, or a good network of observations for the coastal currents. And he initiated this project with this financial support from MOES through INCOIS to establish a network of coastal ADCPs, Acoustic Doppler Current Profilers, which can profile the currents up to a depth of something like 500-600 meters. So he established a good network both for the west coast as well as the east coast. And the picture what you see here is the locations of these profilers at this moment. Presently we have quite a few number of moorings in the west coast and east coast. You will see two symbols, one circle and a triangle. Triangle represent the mooring is at the shelf location. So shelf means it's something like 150 meter water depth they might have deployed it. And when it comes to the slope, the water depth is something like 1200 meter. So they get good observations, and some places you see that both shelf and slope were there. In fact, for all the locations there were shelf and slope moorings, but this was restricted only to the east coast later due to operational reasons. But these observations, right from 2008, we have quite a good amount of data which describes the vertical structure of the coastal currents. We would say coastal in the sense it goes up to something like shelf break region. So this is an important source of information, and this actually was challenging the numerical modelers, because until then the most important part or most well-known part about the coastal currents were their reversal, seasonal reversal. You have equatorward flow, you have poleward flow. So we can simulate, if we can simulate this reversal right, That itself was a good achievement. But with the availability of this data of something like even very high frequency, as high as something like 1 hour, is challenging the modelers to get the things right in their models. It's not quite easy, and we have not achieved anywhere near the that region as of now. But still, we have made a remarkable progress in terms of modeling the coastal circulation and trying to mimic these observations. So one example of this observation is shown here. It's a time series of surface current. Surface in the sense we call it 48 meter is the surface current for this one, because beyond above that this ADCP cannot watch. This is a slope ADCP. So the topmost observation layer is 48 meters. So at 48 meter, this is how the observation shows. The black line is the observation from ADCP, and Arnab has kept the observation from Oscar on the top of that. That's the red line. So you can see that there is a lot of variability, but the most prominent thing, of course, is the seasonal cycle, annual cycle, that we have poleward flow and equatorward flow, and all these are from the east coast. So this is very prominent, but you can also see that there is a lot of variability in a shorter time scale, from shorter than intra-annual time scale. You have intra-seasonal time scale variability and even higher frequency. But if you look at the Oscar currents, you don't find that kind of variability. Of course, Oscar has its own limitations. It's a specially averaged one, whereas this observation is a point observation. But the good thing is that if you look at the slope currents, yes, Oscar is doing a fairly good job in terms of getting the large scale circulation of the Bay of Bengal, at least the western boundary current. So now Arnab also has done an interesting work. He compared the quality of simulations from a complete general circulation model, a much higher version of the model which Vinay was using in 1996. This is MOM4 P1 now. It's a very good model and at a very good resolution of something like 10 kilometer. And he also used a LCS model. So basically he was trying to use an improved setup of what people were using in 1990s. And what is quite interesting is that, again, what you see in the right hand side is the comparison of observation and the models. You have black line, what is the observation, and then we have red and green, which are two models. One is a complete general circulation model, which has all nonlinear terms in that one, and we have an LCS, which is green, that is having only the linear part of this one. The interesting part is that, of course, to large extent, the models are able to simulate the annual cycle, and both models, whether it is LCS or MOM, the simulations, quality of simulations are not very different. They do quite good job. So at least in the annual cycle period. So this gives again an indication that, okay, we are looking at something very unique. The high frequency variation is not yet simulated by the model to the extent what it should have, but it's doing a remarkable job in terms of low frequency variability. So this was an interesting study by Arnab and co-authors. Now, since we have observations from ADCP, which we know that is giving the vertical structure also, because we did not look at the vertical structure of the current so far. Most of the studies were looking at the surface or whatever available at the top layer. So here, if you look at the ADCP observation from 4 locations, Gopalpur, Visakhapatnam, Kakinada and Kadalur. So these are the 4 locations which are marked in this graph. And what is interesting is that, okay, Gopalpur, we are seeing this seasonal reversal, that's good, but we are also seeing that there are quite strong undercurrents. The surface current and the subsurface current may not be in the same direction. So this is also an interesting observation which Shetty had already noted in 1991 paper that there are possibilities of undercurrent, particularly in the summer season. So this was confirmed by these observations. We have undercurrents, and quite strong undercurrents in quite many places. And if you look at the variation of undercurrents, okay, we have good strong undercurrents in Gopalpur, but the depth at which we see may be something like 200 to 300 meter and or below that. Then Vishakhapatnam also has a little variability in the undercurrents, and this also is quite deep, maybe around 200 meter. And then comes to Kakinada, we don't have much variability, and of course observation is also has limitations there. But you can see that compared to other two locations, Vishakhapatnam and Gopalpur, Kakinada has relatively low variability in the currents, along shore currents. On the other hand, a southern location, Kadalur, which is close to Chennai, it has quite a lot of variability in the undercurrents. Of course, we have surface currents in one direction and subsurface current in another direction. But even the subsurface current is having very high frequency variability. This observation is for 2013 and 14. You can see that same variability in both the years. And on the top of that, we have a seasonal envelope on that. So this was quite interesting. Another observation with this data is that in Kadalur, these undercurrents are quite shallow. Something like 100 meter onwards, you start seeing that the poleward flow below the equatorward flow in the surface. So this is also an interesting feature. So we got a little excited with this observation of Kadalur. One good thing is that we have good data of that, and also we would like to see how models are doing this. Now, this is the time in which INCOIS has been getting request of accurate forecasts of coastal circulation. So we have come up with an ambitious project of setting up a high resolution operational ocean forecast and reanalysis system. This has been put in place now, and it's a very complex system, but the core of the system are basically two models, basically a single model with two configurations. One is an Indian Ocean configuration of ROMS model. This is having a resolution of 1/12 degree. And another one is a Northern Indian Ocean model that is having a resolution of 1/48 degree. So remember, the Indian Ocean model has something like 9 kilometer resolution, whereas the Northern Indian Ocean model has a resolution of something like 2.25 kilometer. So it's a very high resolution model for the northern part. Of course, northern part model had components initially. We had a separate setup for the west coast and the east coast, but later we combined it. But most of the next slides in the coming slides, I will be using the simulations from this setup, which is shown in the blue box. This is the Bay of Bengal setup of the ROMS. It also has a resolution of 1/48 degree resolution, and we have done extensive validation of different parameters, temperature, currents, coastal currents, equatorial currents. All those things are done extensively, and if any of you are interested to see, please read this particular paper in Bulletin of American Meteorological Society published last year. Say total description of the system. But I wanted to show how the models perform in the equatorial region. So this is the simulation and observation from an equatorial location, 80.5 degree east and equator. The model is the same one which I was talking about. The basin scale Indian Ocean ROMS has a resolution of 1/12 degree, about 9 kilometer resolution. So the top panel, what you see here is the observation. So equatorial current, I am not going to the details of equatorial currents or its dynamics, but what you see is that, okay, there are occasions on which equatorial currents are quite strong and flowing from west to east. You see positive values. Then we have something like a westward flow, and then intermittent westward flow. Then again we have strong flow. So this is quite known to us as murky jets in the Equatorial Indian Ocean. You can see that the model is doing a fantastic job in simulating not only the surface current. The currents what I have plotted here is from surface to or 50 meters to 250 meters. You see that model is doing a remarkable job. And if you look at the surface current at 50 meter, surface in the sense 50 meter, see that the model is doing extremely good in terms of getting the zonal currents. Except one or two occasions where the model was slightly off, that too when the currents were weak. Otherwise, the model is doing a good job. This is the state of the art model we have. And remember, if you use any other model, also equatorial currents are going to be simulated fairly well by those models. But when you use the same model, that is something like 1 by 12 degree, that is 9 kilometer model, and try to see what happens for the coastal circulations. This is again that location I was talking about, Kadalur locations near Chennai, and see how the observation and model. You get an annual cycle. Naturally, you get an annual cycle. You have a poleward flow, then you have an equatorward flow. You have a slight undercurrent, not very prominent, or it does not have much variability. Again, you have poleward current and then equatorward current. So this annual cycle has come up quite good. And another location in the central Bay of Bengal. I think this latitude and longitude is wrong. Actually, the longitude is 90 degree east at 12 degree. This is a Rama mooring. So this one also is not doing a great job. It's in Bay of Bengal, central Bay of Bengal. Of course, to some extent model is matching with the observation, but there are occasions on which it has gone way off also for some reasons which we already know what are the difficulties of this model. But you can see that this even if it's called a high resolution, 1 by 9, 1 by 12 is a pretty good resolution for the tropical ocean, but still these models are not able to capture the coastal currents or even the central Bay of Bengal currents to a good extent. So at this point we thought, okay, now we have this high resolution model, so we set it up for the operational purpose. And the model is again ROMS. I have given a little more details of this model because we will be talking about the simulations from this model in the next few slides. So this model has a vertical 40 sigma vertical levels. So sigma levels means they are terrain following. We have options to stretch the vertical coordinates so that wherever we require high resolution, we can get it. So that's a good model for coastal applications. And then we have a resolution of about 2.25 kilometer, quite high in terms of circulation models, ocean circulation models. And the physical options I have chosen are given here, the mixing parameterization scheme, and then air-sea flux computation in the model. And the important part is that since our interest is to look at the coastal circulation, we need to get the tides right, because most of the part the tides are quite important. So we have fine-tuned the tidal component of this model. We have 10 constituent tidal forcing at the boundaries, and then not only the tidal forcing, we give realistic boundaries condition from the Indian Ocean high resolution ROMS model to get the tracer and momentum right. And we have done this on a daily scale so that there is a very high frequency interaction between the Equatorial Indian Ocean and this domain. And you can see that tides are fine-tuned. Both the barotropic and baroclinic tides are doing getting simulated extremely well in this model. There were several articles which we published using this model and looking at the tidal characteristics of the Bay of Bengal. So this model is doing a remarkable job in terms of both tidal as well as the subtidal circulation. This is the kind of again an animation of circulation in the Bay of Bengal, which we have simulated using this high resolution model. You can see that the Bay of Bengal, as you have seen in the observation, is dominated by eddies, and most of the boundary current is influenced by these eddies. You can see that quite well. You can see that by March we get the EICC poleward EICC established, and quite strong, much stronger than observation. This is one difficulty in this model, of course. And then you started seeing that signals start to reverse in the northern part with the arrival of Kelvin waves, and then slowly we get the EICC flowing a little to the southward. That is bringing the fresh water to the south, which we all know how the Bay of Bengal fresh water is getting transported to the Arabian Sea. So this part of the circulation is well simulated. Of course, the strength of the circulation is a little higher than the observation, but the basic features of the circulation both in the open ocean and the coastal circulation are simulated very well by this model. So we thought, okay, this is a good model, and then we can look at what could be the structure of coastal currents. Now we have observations from the ADCPs, and now we have a good model, fairly good model with a very good resolution. So let us see how good these models are simulating the vertical structure of currents in this coastal. Again, our interest is along shore currents at the slope location, not in the shelf now. So what you will see here in the figures is that, okay, we have observation from Gopalpur. I have marked it as A, the top left one, and just below that is the Gopalpur model. So the along shore current extracted from the Gopalpur buoy location is from the model is plotted here. It's doing a great job. In fact, the vertical structure is simulated very well. We get, of course, the annual signal is there. Plus, we have these undercurrents with reasonably good variability. The model simulates the variability. And more interesting is that the depth at which these undercurrents are seen are also well simulated by the model. When you come to the subsequent panels, you will see that this changes with latitude also is getting reflected in this model quite reasonably well. And the second part is Visakhapatnam, just south of Gopalpur. Again, we get it fairly good. Of course, the high frequency variability in the Visakhapatnam is not as spectacular as what we see in the southern part like Kadalur, but it has a variability, and model is able to simulate that, and model is showing the undercurrents with a reasonable good accuracy, much better than what we saw in the low resolution model. And then Kakinada, and we have noted earlier also, Kakinada currents are not very, the variability in the currents are not strong, and of course observation is also a little sparse. And model also shows the same thing, that okay, the variability is relatively low in the along shore currents. It's basically dominated by the annual cycle with little changes during the monsoon season. Then comes the Kadalur. This is where we noted that the undercurrents are seen at a little shallower depth, and you can see that the observation model also shows that the undercurrents are at shallower depth, and the timing of the undercurrents are perfectly good, and the intensification of the subsurface currents are also quite good. Annual cycle is good. We see the variability quite well, and you can see that overall the simulation of undercurrents are far superior than that 1/12 degree model. So this encouraged us to look at, okay, what could be this high frequency variability in the coastal current? What could be forcing this? And now we have a model which is simulating a reasonable things in a reasonable good shape. So let us see the dynamics behind these undercurrents. I'm not generalizing this that all the features you see in the undercurrents are can be explained with the explanation what I give in the subsequent section, but a few cases where the model simulated well, for example the case which you see in the October, November, December or November December part of 2014. So such cases we try to explain whether it has something to do with the large scale circulation or it's a very local system. So this is what we try to address in the next few slides. So what I have plotted here is now we have the model, so we know we have all four-dimensional structure of the circulation. So what I have plotted here is a depth longitude section, that means a cross section of currents, and this is at the location where we have that ADCP. It's at 12 degree north. So as we go away from the coast, what you see in the gray color is the coastline and the land part. So what you can see is that away from the coast we have very strong EICC flowing southward, and below that we have a substantially strong undercurrent. It's something like 1500 meter we have at a core of this EICC, but it's a bit far from the coast. It's at a water depth of something like 2500 meters, and this is far from our observation also. Our observation, shelf observation, is at where I have this blue dot, and the slope observation is I have this red dot. So if you look at that in the slope observation, we were looking at the slope observation, we can see that of course we have a strong current flowing southward. This is the EICC, and below that we have a small intense poleward flowing current, which has its core somewhere around 200 meter or something like that, less than 250 meters. This is an interesting observation. Similar observation we have for the December event also, but we don't see that the strong patch as spectacular as what we saw in the November, but it's still there, and the pattern is quite good. We have the strong EICC away from the coast, and there is a strong undercurrent. We are not worried about this undercurrent because we did not observe it in the ADCP. We observed this part only in the ADCP. So I'm going to focus on this part that happened, that is at the buoy location or ADCP location. So what I have shown here is the snapshots of that December event, which I have shown in the previous slide. We have surface currents, the background is the speed, and you have the arrows on the top of that which gives the direction of the current. And then we have 150 meter, 200 meter, 250 meter, 500 meter and 1200 meter. This is how I have plotted the things. And you can see that the surface currents are quite strong and flowing southward. This is what we saw in the earlier diagram also. But when we come to the bottom or 150 meter, a little low, you can see that the surface current intensity has come down. At the same time, we started seeing a small anticyclonic circulation to the right of the flow, or to the shoreward side of the flow. We started seeing a small anticyclonic circulation, and this gyre has intensified further when we went to 200 meter. And 200 meter you can see another anticyclonic gyre far away from the coast also. But by 250 meter both these started coming together, and then by 500 meter we can see that only one large anticyclonic gyre what we saw in the what we see in the observation and model, sorry. And then 250 meter is again the same thing. But remember, these color scales are different for different, because as we go deep the magnitude of current comes down. So to adjust to make it easy for eyes to follow, we have increased the color levels in the bottom levels. So this is how the currents we looked at. So we have, if you look at the surface, we have a strong poleward current. At the same location, if you look at the subsurface, we have an at the surface we have a strong equatorward current, and if you look at the subsurface we have quite good strong poleward current. This is the undercurrent which we have seen, and it has merged with the large scale circulation after some depth. This is that kind of advantage we have with the model. The model gives all the terms of momentum equation so that we can balance it. So we have computed a momentum budget of along shore current at 200 meter depth, because that's where we saw the core of that small eddy. We call it as a very small scale eddy because the length scale is of the order of something like 40 or 50 meters only, kilometers only. So most of the time we have balance is between the Coriolis force and pressure gradient force when there is a eddy kind of situation. So when we were looking at this November-December event, you can see that the black line, which is the pressure gradient force, and the blue line, which is the Coriolis force, is getting balanced in most of the time, and the acceleration in the larger time scale is quite low. So it's mostly in a geostrophic kind of a balance, because we have a eddy, anticyclonic eddy and that location. So once we have an eddy which has a circular motion, okay, now let us track what does it say. If you have a circular motion, that means it has a relative vorticity. So what does the vorticity say? And we know that the vorticity, in this case we are looking at the alongshore currents only, and the latitudinal variation of alongshore current at this location at least is quite low, so we just ignored that latitudinal variation of u, whereas we considered the longitudinal variation of v, which is basically the shear component. So alongshore current at one location minus alongshore current at different location divided by the distance between these locations gives basically the vorticity at that depth. We looked at it to 120 meter, and what you see is that of course I have plotted the observation of alongshore current at the shelf from the ADCP and from the slope. You can see that there are undercurrents, but you don't see that kind of a strong undercurrents in the shelf location. But in the slope location you see it. Very interesting point is that it's at shallow depths. And model also has that, but when we look at much closer, we see that there are slight discrepancy in the depth, but still the model is showing that quite realistically. And the timing also is not very bad. Wherever there is undercurrent, strong undercurrent in the subsurface, we see that undercurrent in the model also. And the interesting part is that the variability of this vorticity, what we computed, is basically following the variability of the currents in the slope location. So that means we have the variation in the currents away from the slightly away from the coast, or the core of the EICC is actually determines the variability of the undercurrents, which gives an indication that the intraseasonal variation in the alongshore currents or the EICC must be the driving factor for the initiation of this small scale eddies. It must be coming out of the shear of this EICC. That's what we could understand from this analysis. Why we did not get this right in the low resolution model? We got it good in the high resolution model, but we did not get right in the low resolution model. So the problem lies here. This is the topography of or bathymetry of the model, and you can see different curves. One is the E-topo, which we used for the model, whether it is low resolution or high resolution. We used E-topo to give the topography of model. And then we have two model setups, 1/12 and 1/48. So when it goes to the E-topo data goes to the model, it interpolates into its grid. So 1/12 has interpolated into that grid, and 1/48 has interpolated into that grid. Then we have another observation, SRTM, and we can see that SRTM and at least in the shelf region, SRTM and E-topo are not very different. The interesting part is that the bathymetry is well represented in the high resolution model, but not in the low resolution model. You have very gentle bathymetry in the low resolution model because of the interpolation issues. So this is a big issue, because we are looking at the shear of EICC, and this shear is basically coming from the interaction between the mean flow, that EICC, with the bathymetry or the coastal bathymetry. And if you have a very smooth bathymetry, the shear is going to be very low, and you are not going to get the that anticyclonic jar there. So this is what prevented the low resolution model to simulate that undercurrents reasonably well. This is there. This is a problem not only at this location. If you go to a northern location also, you find the same problem. And if you look at the difference between this topography, well, at the location where we looked at, the difference is quite low, but there are regions where we have very large difference in terms of depth, because once you slightly move in this shelf break region, the topographic, the bathymetric depth can be very different. So this can actually lead to a large difference in the simulation of the subsurface flow. So bathymetry plays an important role. I'm just showing an interesting research recently published by Bishomoy et al. They also talk about the role of bathymetry. Actually, they say that okay, shelf break or the something which is to the shelf is going to act as a something which is near to the coastline is going to act as a high pass filter. So it support only the high frequency variability part, whereas the bathymetry away from the coast is going to act as a low pass filter. So there is a natural filter which is going to do a band pass for the signals. So if you don't get the bathymetry right, or if you don't represent the bathymetry right in the models, it's going to create issues. This is another slight analysis which we have done to see the importance of bathymetry, and this is slightly different output. This is a temperature output at a location near Andaman Islands. It's slightly west of Andaman, but you can see that it's a coastal buoy. The water depth is only 10 meter. And you have two models. One is a low resolution model and another is a high resolution model. Both models are same what we discussed earlier. You can see that the high resolution model is doing an exemplary job in terms of getting the intraseasonal variation in temperature at 3 meter, whereas low resolution model is only getting this large annual cycle there. Only a slight part of the intraseasonal variation is getting simulated by this model. So we again looked at that and we found that when we interpolated the bathymetry to 1/12 degree, it has deepened the ocean, and we have a water depth of about 60 meters, whereas the actual water depth is only 10 meter. High resolution model gets it right, but low resolution model makes it much deeper. And if you have a large deeper mixer layer, we know that the entire heat flux term which comes into the ocean is going to get mixed up in that water, and the variability is going to be much low compared to the shallow mixer layer. So this is another important example of accurate representation of bathymetry in the at least for the coastal application. There was a paper recently published in Ocean Modeling by comparing different model simulations, and they have come up with a statement that refinement in model resolution does not significantly improve the simulation, because they were looking at a basin scale feature, large scale features. But the statement has to be a little taken with a little more cautious, because as I have shown in the previous slides, when it comes to the coastal applications, resolution matters, bathymetry matters, and different coefficients and viscosity parameters. These all things are extremely important when it comes to the coastal application. So we have to see the context in which the paper is talking about. So let's come to the conclusions. So what we can say that the state-of-the-art high-resolution models can now simulate the shorter term variation in the coastal circulation with a fairly good accuracy. Of course, we have to go much far to get it accurate enough to say that okay, tomorrow current is going to be northward or southward, but we can say to a large extent that okay, it's going to be in this direction most probably. And part of the high frequency variation of undercurrents of Equatorial should be associated with mesoscale circulation and its interaction with the coastline and bathymetry. And high resolution circulation models may not be improving the simulation of the open ocean features, but certainly improve the simulations of coastal circulation. And it's important, that's the critical point of this talk, that accurate representation of bathymetry is very critical in the simulation of the coastal circulation. So thank you. I will stop here and I will see whether we have any questions in the live chat. Okay, there is a question asking is there any circulation So the question is that is there any circulation model that gives better results for coastal lagoons. See, the problem with most of our circulation models as of now is that accurate representation of bathymetry in such regions are it's a question, and we need to get a good bathymetry. And when it comes to very close to the coast applications like lagoons or estuaries and all, we know that the coastline structure of coastline is very complex, and the models which we are using right now may not be suitable for that because they are using finite grid. So a finite volume with a flexible mesh could be a much more efficient model for that. There are several such modeling efforts going on. There are a few in the research mode, and in fact INCOIS is also now developing very close to the coast or estuarine modeling framework based on a finite volume model. So this can come up in the next couple of years. So this is the answer to that questions. Okay, I'm not seeing any more questions. Okay, just a minute. Okay, so another question is, can you compare the Cuddalore with Andaman Sea? Do you find anything interesting patterns? So, of course, my comparison was, my intention was not to compare Cuddalore with Andaman Sea. My intention was to show that in both locations, whether it is Cuddalore or Andaman, close to the Andaman Sea, bathymetry plays an important role. So I have not looked into the circulation, whether both the regions have some similar circulation patterns. So that part I have not seen, but I can presume that the Cuddalore, being in the western boundary of the Bay of Bengal, the dominant currents must be the EICC. So that may not be there in the Andaman Sea. So there could be differences, but I have not, my intention was not to compare these two circulation. In fact, if you look at the slide, you will see that the one was current, and when it went to the Andaman Sea, that the comparison was on temperature, not on currents. So another question is why the Gopalpur underwater current is high. So we have looked at this, and what we found is that the subsurface anticyclone of Gopalpur was quite strong. It was much stronger than the southern part. So that could explain this. But again, we know that there is a lot of forcing coming from the equatorial Indian Ocean in terms of coastal Kelvin waves, and probably in the northern latitudes that may get latitudes circulation may get affected much stronger by this coastal circulation, the coastal Kelvin wave, than the southern location. And also Cuddalore is a unique location because of its coastline structure. So it has a concave shaped coastline structure. So that may one of the reason why the Cuddalore currents are slightly different from other locations. Okay, another question is sea level variation study is also affected by the resolution. Which model is the best? So the question here, which model is the best, is a question which we often hear from researchers. There is no best model. Actually, models are only tools. So for what purpose you use is the more important problem. If you remember the slide which I have shown with a very complex modular ocean model and a very simplified LCS model, Arnab has shown that both the models are showing similar kind of variability in terms of annual cycle. So the important part is that what you are looking at. So if you are looking at something which is very close to the coast sea level changes, then we need several things right in that model. Maybe a finite volume model may be good uh, if you are very close to the coastline, or if you think that okay, somewhere in the slope you are interested, then probably the models with sigma coordinate system like ROMS is a very good option for you to choose. But whatever be the reason, models are only tools, and it's like a camera in your hand. Even if you have an expensive camera, if you don't know how to use it, then there is no use. Okay, there is one more question we have, is that what are the challenges in identifying the signature of climate change in coastal circulation in numerical models? Well, this is an interesting question because we are talking about climate change. See, the most important part of the climate projections are that we are still working with relatively low resolution models in the global oceans. Probably if you want to come very accurate sea level projections, say for a city or something like a state, then we may have to downscale them. So the first challenge is that how to dynamically downscale these models, large scale models, to the coastal applications. That's a challenge. And then we need to force these models with some atmospheric forcings. So if you look at the atmospheric component of the climate models, which gives projections, they are even coarser than the ocean component. So how to downscale the atmospheric forcing is another question. And I have heard that there are efforts in the global community to use AAML techniques to downscale these, and there are other research which is going on in terms of using EOF analysis to identify the leading modes again in the climate projections and reconstruct them into high resolution forcing for the coastal applications. So these are all challenges in this part of the studies. So it's going to be quite challenging. And again, when it comes to the accurate projections of sea level, you need to have a good bathymetry, you need to have a good topographic data. Fortunately, we have that for the Indian coast due to our mapping for tsunami vulnerability and multi-hazard vulnerability. So that could be a good advantage when we plan to project the sea level scenarios, at least to the present state, not to the future. Well, there are quite a good questions now. How does undercurrent form in the coastline? Probably if you can look at the see the video of this lecture once again, you will come to know that okay, there are different mechanisms. One of the mechanism only I have mentioned, that a few particular events were actually part of small scale anticyclonic circulations. And when we have looked at the northern part, we found that they are part of large scale anticyclonic circulations. That's what I was mentioning in the previous question. So there could be different reasons, and there are good studies which shows that the equatorial forcing also shows this undercurrents. And there are phase propagation which you can see in a little longer time scales. The question is, another question is river discharge is included in the model? No, this model does not have river discharge. Surface salinity is relaxed to climatology. So that's what I was telling, that we know that technical problems or the limitations of the model. That's why I cautioned you that these are only studies, and we looked at only when things looked good. There were many cases where things were bad. And particularly when we come to the coastal circulation, yes, salinity plays an important role. So it is no doubt that we have to include river discharge in these models, but including river discharge to an operational model is a challenge, because most of the time what we have is a climatological river discharge, or to some extent some satellite derived sea level, based on the sea level altimetry data. They have given some monthly river discharge data. It's a kind of derived one, but all these things applying for an operational system which has to give forecast in a daily basis, not very easy to do. So most of the operational agencies either do a relaxation or incorporate the effect of river discharge in precipitation or something like that. Okay. So another question is that, can we get some more information particular to Gopalpur location? There are a few studies on East India coastal current by Mukherjee et al. And a couple of students from Dr. Shankar's group. So those studies may be very useful. In fact, one of the studies shows that we were looking at the currents from 48 meters, but when we have when they have looked at HF radar data, they found that the surface currents up to 20-25 meters are not flowing in the same direction that we have seen in the ADCP observations. So whether there is another surface flow on the top of this is something which we have to look at that. So there are quite a lot of interesting studies from NIO Goa. I would suggest that you can go through those publications. Okay, another question is that, is it possible to model ocean current data collected for a period of 10 days using ADCP, and which model is best for that? Well, I don't know the context of the question. As all these models can simulate for 10 days, that's not a problem. But if you are only looking at initiate a model and just run for 10 days, I would suggest that with the dynamics of Bay of Bengal, this may not be a good option, because you need to get the equatorial forcing right. You need to get the forcing from the interior Bay of Bengal, and well, if you have a good boundary condition and if you can get accurate boundary values, then we can do a small scale setup of maybe ROMs or FECOM. But it's a challenge to get all these things right, because you are looking at running a model only for 10 days. So all these are research problem. I'm not saying that it is not possible, but you need to work on that. Another question is for alongshore current and sediment transport modeling, you said critical consideration of bathymetry SRTM or JEPCO can use for better results. Yes, SRTM or JEPCO are good options. Yeah, we have done some experiments with SRTM, and see, when you are looking at large scale features, they may not look very different. But I understand that SRTM and JEPCO are fairly good data sets. We can try that. We did not do that. Maybe when we go for this very high resolution coastal simulations, we will use such bathymetry data. Did you observe the influence of inland drainage on the coastal circulation model? Well, we have not gone into that details. I said my interest was mostly on the slope area, because even I have not looked carefully about the shelf data, because I'm sure that model may not be doing an extremely good job in shelf. We need to look at other dynamics. So I have not looked at any plume dynamics, or even I told river discharge is not included. So yeah, these are important problem, and these are important problems for operational oceanography. I'm sure that we will address such things also in the coming years once we have very high resolution finite volume model, which we are now building as part of our new ocean modeling mission initiated at INCOIS. Okay, I don't see any more questions, so thank you all. Thank you very much for listening to this talk, and very good questions from a lot of viewers. I thank them all, and in fact all these questions gave me an opportunity to think, and you people have given us guidance on what to do in future. Thank you very much. That was very useful for me also. Thank you for watching this.